Something in our solar system is pointing at the sun with a precision that defies natural explanation, not drifting, not wobbling randomly through space like every other comet we've ever observed, aiming, tracking, maintaining a lock on our star with an accuracy that has less than a 1 in 200 chance of occurring naturally. And right now, as you're watching this, that object is making its closest approach to Earth, giving us a narrow window to understand what we're actually looking at. This isn't science fiction. This is happening in December 2025, documented by some of the world's most advanced observatories and analysed by scientists including Harvard's Dr. Avi Loeb, who've spent their careers studying objects that wander through our cosmic neighbourhood. What they're seeing breaks the fundamental rules of how comets behave. It violates the basic physics that govern every natural object we've encountered in space. And the mathematical probability that this alignment happened by random chance, 0.5%. Think about that number for a moment. Imagine flipping a coin and needing it to land on its edge, balanced perfectly, 200 times in a row. That's the level of improbability we're dealing with. This isn't a marginal anomaly or a slight deviation from expected behaviour. This is an object performing manoeuvres that our current understanding of celestial mechanics says shouldn't be possible without deliberate orientation control. You've probably heard whispers about unusual objects entering our solar system. Maybe you followed the Oumuamua controversy back in 2017, when Harvard professor Avi Loeb suggested that cigar-shaped visitor might have been something other than a natural asteroid. Maybe you remember the debates, the skepticism, the scientific establishment pushing back against any suggestion that we might be looking at evidence of extraterrestrial technology. But what if I told you that what we're observing right now makes Oumuamua look ordinary by comparison? The object we're talking about is called 3I Atlas, and it represents the third confirmed interstellar visitor to enter our solar system in recorded history. It came from beyond our sun's gravitational influence, travelling through the vast emptiness between stars before crossing into our neighbourhood. And from the moment professional astronomers began tracking its movement, they noticed something deeply wrong with how it was behaving. Stay with me for the next several minutes, because we're going to walk through exactly what Dr. Avi Loeb and his research team have been observing, why it contradicts everything we know about natural comets, and what that 0.5% probability actually means when you break down the geometry and physics involved. This isn't about speculation or wishful thinking. This is about hard data, precise measurements, and asking the uncomfortable questions that emerge when the evidence doesn't fit our expectations. Here's what makes this so significant. When scientists observe comets, they work with well-established models of behaviour. Comets are essentially dirty snowballs, ice and rock that heat up as they approach the sun. That heating causes gas and dust to spray off their surface, creating the beautiful tails we associate with these objects, and those tails always, without exception, point away from the sun. Why? Because the sun's radiation and solar wind push that material outward, away from the star's surface. It's basic physics, observed consistently across thousands of comets throughout human history. But 3I Atlas developed something that astronomers have started calling an anti-tail, a jet of material pointing directly at the sun, not at an angle, not swept back by solar wind, aimed at our star with a precision that becomes more unsettling the longer you examine the observations. And this jet didn't just appear briefly and then dissipate. It maintained that orientation as the object travelled through space, as it swung around the sun in late October, and as it continues its journey outward from our solar system right now. What you're about to see in the data is something that challenges our fundamental understanding of how natural objects move through space. We're not talking about vague anomalies or debatable interpretations. We're talking about measurable, documented behaviour that Dr. Avi Loeb has identified as 14 separate anomalies inconsistent with known natural processes. 14 distinct observations in his analysis, each one raising questions that become harder to answer with conventional explanations. And the most disturbing part, the closer Loeb's team analyses the data, the more precise that sun-pointing alignment becomes. The object's rotation axis, the direction of its jet, the timing of its wobbles, everything seems calibrated to maintain a specific orientation relative to our star. If you were designing a probe to keep one side perpetually facing the sun while rotating, this is exactly what you would engineer it to do, so here's what we need to understand together. We're either witnessing the most improbable natural alignment in observational astronomy, or we're looking at something that was designed to behave exactly this way. And with every day that passes, with every new observation that comes in, that 0.5% probability becomes harder to dismiss as coincidence. If you're as curious about this as I am, hit that like button and drop a comment telling me, do you think 0.5% is close enough to zero to start asking serious questions about what we're observing? Because what we're about to explore together might fundamentally change how we think about our place in the universe and whether we've been alone all along or simply not looking carefully enough at what's been passing through our solar system. The investigation begins with understanding what 3I Atlas is and why scientists immediately recognized it as different from anything they'd seen before. When you think of comets, you probably picture those stunning images from space telescopes showing graceful tails stretching millions of kilometers behind icy cores. You might remember Halley's Comet, or Hale-Bopp, or any of the dozens of comets that have captivated human observers throughout history. These objects follow predictable patterns. They orbit the sun on elongated paths, heating up as they approach, cooling down as they retreat, their behavior governed entirely by gravity and basic thermodynamics. We've studied comets for centuries, and while each one has unique characteristics, they all operate within well-understood boundaries of natural physics. 3. I-Atlas shattered those boundaries from the moment it entered the observational record. The designation itself tells you something important. 3I means this is the third confirmed interstellar object we've detected entering our solar system. The first was Oumuamua in 2017, that strange elongated object that accelerated away from the sun in ways that puzzled scientists. The second was 2I Borisov in 2019, which behaved much more like a typical comet and actually provided reassurance that most interstellar visitors follow normal rules. Then came 3I Atlas, and any comfort we'd gained from Borisov's conventional behavior evaporated. Interstellar objects are incredibly rare detections. Think about the scale involved here. Our solar system is a tiny island in an ocean of emptiness. The distances between stars are so vast that an object travelling from another stellar system takes hundreds of thousands of years to cross that gulf. The fact that we've now confirmed 3 such visitors in just 8 years suggests either we've gotten dramatically better at detecting them, or there are far more of these wanderers than we previously imagined. Either way, each one represents an extraordinary opportunity to study material and dynamics from beyond our sun's influence. But 3I Atlas didn't just present an opportunity for study, it presented a challenge to everything we thought we understood about cometary physics. From its earliest observations, astronomers noticed irregularities. The object was bright, suggesting significant outgassing activity as volatile materials vaporized off its surface. That brightness made it easier to track than many interstellar visitors, which often remain too faint for detailed analysis. So in one sense, we got lucky. This particular visitor was visible enough that professional observatories could dedicate serious resources to watching its behavior. And watch they did. Multiple telescope networks tracked 3I Atlas as it made its way through our solar system. The data started accumulating: trajectory measurements, brightness variations, spectroscopic analysis of the gases surrounding it, standard scientific protocol for analyzing any comet. But as those data sets grew, patterns emerged that Loeb and his collaborators identified as not matching expected templates. The brightness fluctuations weren't following expected curves. The trajectory showed subtle variations that suggested something more than simple gravitational influence and gas venting. Here's where you need to understand something fundamental about how comets move. When a comet approaches the sun, frozen materials on its surface heat up and turn directly from ice to gas, a process called sublimation. That gas carries dust particles with it, creating a cloud around the comet's nucleus called a coma, and forming the tail we see stretching behind it. This outgassing doesn't just create visual beauty, it actually affects the comet's trajectory. The expanding gas acts like tiny rocket thrusters, pushing the comet slightly off its purely gravitational path. Scientists call these non-gravitational accelerations, and they're completely normal and expected. What's not normal is when those accelerations seem coordinated or directional in ways that pure physics shouldn't produce. Comets are irregular chunks of ice and rock, not engineered objects. Their outgassing should be chaotic, driven by which parts of the surface face the sun at any given moment, modulated by the comet's rotation and the varying composition of different surface regions. You'd expect randomness, or at least variation that averages out over time, you wouldn't expect precision. 3I Atlas displayed precision. As scientists analysed its trajectory and the jets of material emanating from it, they found patterns that suggested something beyond random outgassing from an irregular rotating body. The jets weren't scattered in multiple directions as you'd see from a typical comet. There was a dominant jet unusually collimated, meaning tightly focused into a narrow beam, and that jet maintained a consistent orientation that seemed decoupled from what the object's rotation should produce. Think about spinning a garden sprinkler. The water sprays out in all directions as it rotates, creating that characteristic circular pattern. Now imagine a sprinkler that somehow kept one of its jets pointed at a specific spot in your yard, even as the sprinkler body continued spinning. That would require the nozzle to be adjusting its orientation constantly, compensating for the rotation to maintain that fixed aim. That's not how basic rotating objects work unless something is actively controlling them, and this wasn't a subtle effect that scientists had to squint at to detect. The antitail jet from 3I Atlas extended across distances greater than the space between Earth and our Moon. We're talking about a collimated beam of material spanning hundreds of thousands of kilometers, all aimed at the Sun, while the object itself rotated with a measured period that should have swept that jet in a circle across the sky. Instead, the jet wobbled in place, maintaining its overall sun-pointing direction. The immediate question from the scientific community was whether this could be explained by the object's rotation axis happening to point toward the Sun. If a comet is rotating like a top, with its spin axis aimed at the Sun, and if outgassing happens predominantly near one of its rotational poles, then you could potentially get a jet that appears to point sunward from our perspective. This wouldn't violate any physics, it would just be an unusual but natural alignment. But here's where the first real alarm bells started ringing. For that explanation to work, the rotation axis would need to be aligned almost perfectly with the direction to the Sun, and that alignment would need to persist as the object's trajectory changed. Remember, comets follow curved paths as they swing around the Sun. The direction from the comet to the Sun is constantly changing as the object moves through its orbit. For a jet to keep pointing at the Sun throughout that journey, something has to adjust. Either the rotation axis itself is changing, which requires external torques and leads to its own set of complications, or there's another mechanism at work. Loeb's research team and other scientists began running models, trying to reproduce what they were seeing using only natural processes. Could uneven heating create torques that reoriented the object? Possibly, but the timescales didn't match the observations. Could the object have an unusual shape that channeled outgassing in specific directions? Perhaps, but the sustained precision of the alignment stretched that explanation thin. What about tidal forces from the Sun, or interaction with the solar magnetic field? Each potential explanation faced challenges when confronted with the actual data, and then the object reached perihelion, its closest approach to the Sun, in late October. This was the crucial test. If the jet's orientation was simply due to a lucky initial alignment of the rotation axis, then the gravitational deflection as 3I Atlas swung around the Sun should have broken that alignment. The object's trajectory would bend significantly, changing the geometry, and any fixed jet should start pointing off target. That's what happens to natural comets. That's what physics demands. According to Loeb's analysis, that's not what happened with 3I Atlas, and that's when he and his colleagues at Harvard started calculating probabilities, a methodology that has generated both interest and skepticism in the scientific community. Imagine standing outside on a windy day holding a candle. The flame doesn't point upward in a perfect vertical line. It bends away from the wind, flickering and dancing, but always pushed in that downwind direction. That's exactly how comet tails work, except the wind is radiation pressure and charged particles streaming out from the Sun at over 1 million kilometers per hour. Every comet we've ever observed obeys this fundamental rule. Tails point away from the Sun. The physics is simple, observable, and has been confirmed across thousands of comets throughout recorded history. So when astronomers began analysing 3I Atlas in detail, and realised it had developed a prominent jet pointing directly at the Sun, it was like watching that candle flame bend into the wind instead of away from it. It violated basic intuition about how forces work in space, and unlike a momentary glitch or brief anomaly that might be written off as observational error, this antitail persisted across weeks of continuous monitoring, documented by multiple independent observatories using different instruments and analysis methods. The term anti-tail itself isn't new to astronomy. In rare cases, comets can appear to have a spike pointing toward the Sun, but this is almost always an optical illusion caused by viewing geometry. When we see a comet from Earth, we're looking at a three-dimensional object projected onto our two-dimensional field of view. Sometimes the comet's dust trail, which lies along its orbital path, can appear to point sunward simply because of the angle we're viewing it from. Move the Earth to a different position, and that apparent anti-tail disappears or shifts. It's a perspective trick, not a real physical jet aimed at the Sun. Astronomers accounted for this possibility immediately when they first noticed 3I Atlas's unusual feature. They checked the viewing geometry, calculating whether the apparent sunward jet could be explained by dust trail projection. The answer was conclusive. No, this was not a perspective effect. The jet's orientation remained consistent across multiple viewing angles as Earth moved in its orbit. Different observatories at different locations on our planet, looking at the object from slightly different perspectives, all saw the same thing, a collimated jet of material extending from 3I Atlas toward the Sun. The jet wasn't diffuse or fuzzy. It showed remarkable collimation, meaning it maintained a narrow profile across enormous distances. Think about shining a laser pointer across a room versus turning on a flashlight. The laser creates a tight beam that stays narrow even at a distance. The flashlight spreads out, its light diffusing into a widening cone. Jets from normal comets behave more like flashlights. The material spreads and disperses as it travels away from the nucleus. But 3I Atlas's sunward jet maintained its coherence across distances that would make even focused beams from natural processes spread significantly. We're talking about a jet that extended farther than the distance from Earth to the Moon, over 300,000 kilometers, while remaining narrow enough to be distinctly visible in telescopic observations. The physics required to create such collimation from natural outgassing is challenging to explain. Gas escaping from a small active region on a rotating comet should disperse rapidly as it travels through the vacuum of space. Without magnetic fields or other confining mechanisms, there's nothing to hold it together in a tight beam. And the jet didn't just exist statically. It showed variations in brightness and intensity over time, which initially gave some scientists hope for a natural explanation. If the jet was responding to changing solar heating as different parts of the comet's surface rotated into sunlight, that would suggest a passive thermal process driving the outgassing. But as the data accumulated, those brightness variations revealed something even more perplexing. They were periodic. The jet brightened and dimmed with a measurable rhythm, like a heartbeat, suggesting it was tied to the object's rotation. Here's where the detective work gets fascinating. When you observe periodic variations in a comet's activity, you can often determine its rotation period, how long it takes to spin once on its axis. For 3I Atlas, scientists measured this rotation period through careful analysis of the brightness oscillations. The object was spinning relatively quickly, completing rotations on a timescale of hours. This is common for small comets, which often rotate rapidly either because of their formation process or because outgassing jets create torques that spin them up over time. But now consider what that rotation means for the anti-tail. If the jet is emanating from a specific active region on the object's surface, and the object is rotating, then that jet should sweep around like a lighthouse beam. From our perspective, watching from Earth, we should see the jet appear and disappear as the active region rotates in and out of view, or at least see the jet's direction change significantly as the source region moves around the rotation axis. That's not what observations showed. The jet maintained its sunward orientation throughout the rotation period. It wobbled slightly, yes, we'll get to that crucial detail in a moment, but it didn't sweep around in a circle as you'd expect from a fixed surface feature on a rotating body. This behavior implied something deeply unusual about the object's geometry or rotation axis. Either the jet source was located at or very near one of the rotational poles, where rotation wouldn't carry it in a large circle, or the rotation axis itself was aligned in a very specific way relative to the Sun. Both possibilities raised uncomfortable questions. If the active region was at a rotational pole, you'd need an explanation for why that particular location was preferentially outgassing, while other parts of the object remained relatively quiet. Comets typically have multiple active regions scattered across their surfaces, activated by solar heating as different areas face the Sun during rotation. Having all significant activity concentrated at one pole would be unusual, though not impossible if the object had a very non-uniform composition. But the alignment possibility was even more statistically troubling. For the rotation axis to point toward the Sun, and for that alignment to remain stable over, the weeks of observation required either an extraordinary coincidence or some mechanism maintaining that orientation. In a universe governed by random initial conditions, you'd expect rotation axes to be randomly oriented. Point your spin axis at the Sun by chance, and you'd expect a probability related to solid angles. Basically, what fraction of all possible directions happens to point sunward? Scientists calculated this probability assuming random orientation, and the numbers were not comforting. But that was just the beginning of the statistical analysis. The real revelation came when they factored in what happened during the object's perihelion passage, its closest approach to the Sun in late October, and how the jet's behaviour changed, or more accurately, didn't change in ways that natural objects should. The antitail persisted through perihelion. As 3i Atlas swung around the Sun at its closest approach, experiencing the strongest gravitational deflection of its trajectory, the jet continued pointing at our star. Think about what that means. The object's path through space curved dramatically as the Sun's gravity bent its trajectory. The direction from the object to the Sun changed by dozens of degrees over a span of days. Any jet fixed to the object's surface should have maintained its direction in inertial space, meaning it would start missing the Sun as the trajectory curved. But the jet adjusted. It tracked the Sun through the gravitational turn, maintaining its aim like a turret tracking a target, like eyes following movement while the head turns. This is the behaviour that finally pushed the anomaly beyond what even generous interpretations of natural processes could comfortably explain. And it's this behaviour that led to the probability calculation that sits at the heart of this entire investigation. Before we get to those numbers, understand that scientists didn't rush to exotic explanations. Multiple research teams ran simulations, trying to reproduce the observations using only natural physics. Could tidal forces from the Sun have reoriented the object during perihelion? The torques required would be enormous and would likely tear apart a loosely bound rubble pile, which is what most comet nuclei are. Could the outgassing itself create torques that rotated the object to maintain alignment? Possibly, but the timing and magnitude would need to be perfectly calibrated in ways that seem implausibly fine-tuned. Every conventional explanation required multiple improbable factors to align simultaneously. The object would need unusual composition, specific rotation parameters, precisely timed outgassing variations, and geometric coincidences all working together to produce what observers were seeing. And even when you stacked all those improbable factors together, the model still struggled to match the actual data's precision and persistence. This is what scientists mean when they talk about parsimony, or Occam's razor, when a simple explanation requires you to invoke 5 improbable coincidences, while a different explanation requires only one unusual assumption. You start seriously considering that alternative. And in this case, the alternative that kept emerging from the analysis was that the jet's orientation wasn't random or passively maintained by natural forces, it was actively controlled. That word, controlled, is where scientific caution clashes with observational evidence. Because control implies intent, and intent implies intelligence, an intelligence of the kind that could construct an object capable of interstellar travel, and precision orientation control would fundamentally change our understanding of our place in the cosmos. So Loeb and his team did what scientists always do when faced with extraordinary claims. They checked and rechecked the data, looking for any conventional explanation that could account for what they were seeing without invoking alien technology. And that process of rigorous analysis led Avi Loeb and his colleagues to calculate the probability that what they were observing could occur naturally, by chance alignment and random initial conditions, without any active control systems. The answer they arrived at was 0.5%, less than 1 in 200. A probability so low that it demands we take seriously the possibility that we're looking at something designed, something built, something sent from another star system, with specific observational goals in mind, and that one of those goals is maintaining a fixed orientation relative to our Sun. But to understand why that probability is so troublingly low, we need to look at the next piece of evidence. What happened to the jet itself as the object rotated, and why that wobbling pattern reveals something profound about the geometry of whatever we're observing. There's a beautiful simplicity to how rotating objects behave in space. A figure skater pulls in their arms and spins faster, extends them and slows down, but the basic physics remains constant and predictable. A child's top wobbles as it spins, tracing out those hypnotic patterns as its rotation axis precesses in response to gravity and friction. These behaviours follow laws we can write down in equations, laws that have never been observed to fail in natural systems. So when astronomers began detecting a periodic wobble in 3I Atlas's anti-tail jet, they initially saw it as a potential key to understanding the object through conventional physics. The wobble appeared as a regular variation in the jet's apparent direction, a slight back-and-forth oscillation that repeated with the same period as the object's rotation. Imagine a lighthouse on a coastline. If that lighthouse is perfectly vertical, its beam sweeps out a horizontal circle, and from any fixed observation point, you see the beam appear, disappear, and reappear at regular intervals. But if the lighthouse has a slight tilt, the beam traces out a cone in three-dimensional space, and its apparent height above the horizon varies as it sweeps around. You'd see periodic variation in the beam's position, even though the lighthouse is simply rotating steadily. That's the kind of effect that could potentially explain 3I Atlas's wobbling jet through natural processes. If the jet originated from a source point offset from the object's rotation axis, then as the object spun, that source point would trace a circle, and the jet emanating from it would appear to wobble back and forth from our viewing perspective. This would be completely natural, requiring no exotic physics, just straightforward geometry of a rotating body within a fax's active region. But there was a problem. When scientists calculated how large this offset would need to be to produce the observed wobble amplitude, and compared that to how precisely the jet maintained its average sun-pointing direction, the geometry didn't add up in ways that made sense for a natural object. The jet would wobble through several degrees of arc, a measurable, obvious variation, and yet its average direction over a complete rotation cycle remained locked on the sun to within a much smaller margin. Think about that for a moment. If you're wobbling by several degrees in each direction, your average position should drift unless something is actively centering you. When you walk a tightrope and wobble left and right, you don't accidentally stay perfectly balanced. You're constantly making tiny corrections, actively working to maintain that average-centered position. The wobble itself is evidence of the balancing effort. What 3I Atlas was doing would be like a tightrope walker wobbling dramatically side to side, yet somehow never drifting from the rope's centerline, never accumulating error, never needing to step forward or backward to recover balance. The periodic nature of the wobble gave scientists precise information about the object's rotation. By measuring the time between wobble peaks, they could determine the rotation period with high confidence. This wasn't a guess or an estimate. It was a direct measurement derived from repeated observations over multiple rotation cycles. And that rotation period became a critical piece of the puzzle, because it allowed researchers to predict exactly how the jet should behave if it was fixed to a rotating surface feature. Here's the geometry that matters. When an object rotates, points on its surface trace out circles perpendicular to the rotation axis. A point on the equator traces the largest circle, moving through space at the highest velocity. Points closer to the rotational poles trace smaller circles, moving slower. A point exactly at a pole doesn't move through space at all, it just spins in place. So if your active region producing a jet is at different distances from the pole, you get different amounts of wobble in the jet's direction. Loeb's team used this relationship to constrain where the active region could be located on 3I Atlas according to their geometric analysis. The wobble amplitude told them the region couldn't be exactly at the pole. There was too much movement for that. But it also couldn't be too far from the pole, because then the jet would sweep through a much larger arc, spending most of its time pointing away from the sun rather than toward it. The observations demanded that the active region be in a very specific zone, close enough to a rotational pole to wobble within a narrow range, but offset just enough to produce the measured oscillation. That narrow zone, that specific location requirement, was the first constraint that started making the natural explanation less comfortable. You weren't just requiring an object whose rotation axis happened to point at the sun. You were also requiring that the single dominant active region happened to be located at the precise latitude on that object, where its wobble would keep it sun-pointing throughout its rotation. That's two geometric constraints stacking on top of each other, each one narrowing the probability space. But the real revelation came when scientists examined how the wobble behaved before and after perihelion. If the jet source was a fixed surface feature, and if the object's rotation axis was maintaining a stable orientation in space, as it should for a rigid body with no strong external torques, then the wobble pattern should remain constant in inertial space. The jet would continue sweeping through the same set of directions relative to the fixed stars, even as the object's trajectory curved around the Sun. That constant wobble pattern would mean that relative to the Sun's position, the jet's behavior would change dramatically as the object swung through perihelion. Imagine you're spinning in a circle, and you point your finger straight ahead at some landmark as you spin. As you walk along a curving path, your finger sweeps through different directions relative to the path itself, even though relative to your own rotating body, nothing has changed. The landmark that was ahead of you is now to your side, then behind you, as your walking path curves. That's what should have happened to 3i Atlas. The Sun should have moved through different positions relative to the wobbling jet pattern as the object's trajectory bent. Pre-perihelion observations should have looked different from post-perihelion observations in predictable, calculable ways. The wobble should have carried the jet farther off the sun-pointing direction on one side, closer on the other, creating an asymmetry that would scream natural rotation axis fixed in space. The asymmetry wasn't there, or more precisely, it was far smaller than it should have been. The jet continued wobbling around a sun-pointing average direction after perihelion just as it had before. The wobble pattern adjusted to accommodate the trajectory change, maintaining the same relationship to the Sun's position even as that. Position shifted dramatically relative to the object's inertial motion. This is where even skeptical scientists started running out of conventional explanations. You could invoke complex tumbling motion, where the object's rotation axis itself is changing over time. That can happen with irregularly shaped bodies in space, where asymmetric outgassing or tidal torques cause the rotation axis to precess and wobble. But tumbling motion is chaotic and complex. It doesn't produce the kind of precise periodic wobble that observations were showing, and it certainly doesn't produce tumbling that just happens to keep reorienting the object to maintain a sun-pointing average jet direction through a major gravitational deflection. You could invoke incredibly specific initial conditions. Maybe the object entered our solar system with exactly the right rotation rate, axis orientation, and active region location, that all these effects would cancel out over the timescale of observation. But initial conditions are random. They're not selected to produce specific outcomes. The odds of randomly achieving the precise set of parameters needed to reproduce the observations kept shrinking every time scientists added another constraint to their models. And those constraints kept accumulating. It wasn't just the wobble. It wasn't just the sun-pointing average. It wasn't just the persistence through perihelion. It was all of these factors together, each one independently improbable, all of them simultaneously satisfied in one object. Statistical independence would suggest multiplying these probabilities together, making the overall likelihood vanishingly small. Even accounting for correlations between factors, the combined probability space remained troublingly narrow. The wobbling jet told scientists something crucial. If this was a natural object, it was operating in a configuration space that represented a tiny fraction of all possible configurations, and that tiny fraction happened to be exactly the configuration you'd design if you wanted to maintain continuous observation of the Sun from a rotating platform. You'd put your instrument near a rotational pole, so it stayed roughly oriented correctly even as the platform spun. You'd align your rotation axis toward your target so the average pointing direction stayed fixed. And you'd accept some wobble as an inevitable consequence of the geometry, managing it with the precision available to your stabilization systems. This is the pattern engineers recognize instantly, but scientists hesitate to acknowledge without exhaustive elimination of alternatives. Because once you start thinking in terms of design, in terms of intentional configuration, you've crossed a line that separates conventional astronomy from something far more profound. You've started treating the object not as a natural phenomenon to be explained, but as a potentially designed system to be reverse engineered. And reverse engineering requires understanding not just what the system does, but what it's designed to achieve. If 3i Atlas is maintaining a sun-pointing orientation, the obvious question becomes, why? What purpose does that serve? What could an interstellar object possibly gain from keeping one face perpetually oriented toward our star? The answer to that question depends on understanding the full implications of the alignment geometry, which brings us to the critical perihelion passage and the mathematical analysis that produced that 0.5% probability. the number that transforms this from an interesting anomaly into something that demands we take seriously the possibility that we're not alone. Imagine driving down a highway at night, your headlights aimed straight ahead, illuminating the road before you. As you enter a gentle curve, your headlights continue pointing in the direction your car is facing, sweeping along the curving road naturally because they're fixed to the vehicle's frame. This is how objects work in space too. A jet emanating from a comet's surface points in whatever direction that surface feature is aimed, and that direction rotates with the object, staying fixed relative to the body's own orientation, even as the body's trajectory curves through space under gravitational influence. So when 3i Atlas approached perihelion in late October, researchers had a perfect natural experiment to test whether its anti-tail jet was simply a fixed surface feature or something more unusual. The sun's gravity would bend the object's trajectory significantly as it swung around its closest approach point. That bending, that change in the direction of the motion, represented a critical test case. If the jet was fixed to the object like headlights fixed to a car, it should continue pointing in the same direction relative to the object's own frame of reference, which would mean it would start pointing away from the sun as the trajectory curved. The numbers involved in that gravitational deflection are substantial. When an object passes close to the sun, the change in trajectory can be dozens of degrees depending on the distance of closest approach and the object's velocity. For 3i Atlas, calculations showed the expected deflection would be significant enough that any fixed jet should become obviously misaligned with the sun's direction after perihelion passage. Pre-perihelion observations would show one geometry, post-perihelion observations would show the jet pointing increasingly off target as the deflected trajectory carried the object away on a different heading. Professional observatories prepared for this test with considerable interest. If the jet behaved as expected for a natural feature, it would help constrain the object's physical properties and give scientists confidence that despite the unusual appearance, they were still dealing with conventional physics. If the jet somehow maintained its sun-pointing orientation through the deflection, that would require explanations involving active reorientation or physics not yet accounted for in the models. The observations came in through October and into November. Multiple telescope networks tracked 3i Atlas through its perihelion passage, monitoring the jet's behavior, measuring its direction relative to the sun, watching for the expected misalignment to develop as the trajectory bent. And what they saw was something that made even the most skeptical researchers pause and double-check their analysis. According to Loeb's analysis of the observations, the jet tracked the sun through the turn. Not perfectly, there were small variations, but far more accurately than a fixed surface feature should manage under conventional physics. The average jet direction remained oriented toward the sun despite the trajectory having deflected by a substantial angle. It was as if those headlights weren't fixed to the car frame at all, but instead mounted on a gimbal that actively rotated them to keep pointing at a specific landmark, even as the car turned. Think carefully about what physics you'd need to produce this result naturally. The object itself is following a curved path dictated by the sun's gravity. Nothing unusual there, that's standard orbital mechanics. But for a surface feature to maintain its orientation toward the sun as the object's trajectory rotates, the object's body must be rotating in space to compensate for the trajectory change. The rotation axis, the spin rate or both, must be changing in precisely coordinated ways that keep that particular surface feature sun-pointing. Torque is required to change rotation. Celestial objects don't reorient themselves spontaneously. If you want to rotate a comet nucleus, you need to apply forces that aren't symmetric around the center of mass. Outgassing jets can provide such forces. This is how many comets end up with the rotation periods they have. Gas venting from one side creates thrust, and if that thrust doesn't pass through the center of mass, it creates torque, spinning up or spinning down the object over time. But the torques required to reorient 3i Atlas during perihelion passage would need to be substantial, precisely timed, and directionally correct to produce the observed effect. The object would need to experience asymmetric outgassing strong enough to torque its rotation by the right amount at exactly the right time, while not disrupting the very jet whose alignment you're trying to maintain. It's mechanically challenging even in principle, and when Loeb's team tried to model realistic outgassing scenarios that could produce these effects, they found themselves requiring parameters at extreme values or invoking highly specific configurations that seemed improbably fine-tuned. There's also a stability question. If you're using outgassing torques to maintain rotational alignment, You need feedback. Torques applied at the wrong time or in the wrong direction would drive the object further out of alignment, not correct it. Natural processes don't have feedback mechanisms. They don't sense misalignment and adjust thrust accordingly. They're governed by local conditions, temperature, composition, solar radiation intensity at each point on the surface, not by global orientation relative to distant objects. Engineers design feedback systems. Nature produces stable equilibria where forces balance, but those equilibria arise from potential energy minimization or symmetry, not from active sensing and correction. When you see behavior that looks like feedback control, where deviations from a target configuration are systematically corrected over time, you're observing either an engineered system or an extraordinarily fortunate arrangement of natural forces that happens to produce the same functional outcome. This is the distinction that began crystallizing in scientists' minds as they analyzed the post-perihelion data. The jet's behavior through the gravitational deflection looked purposeful. It looked like what you'd get from an orientation control system working to maintain pointing stability. And that appearance of purpose, that functional coherence, became harder to attribute to random chance the more precisely researchers measured what was actually happening. Avi Loeb's team at Harvard took this analysis to its mathematical conclusion. They asked a fundamental question. If we assume the object's rotation axis orientation is random, as it should be for natural objects with random initial conditions, what is the probability that we'd observe the alignment geometry that actually exists, not just at one moment, but sustained over weeks of observation and maintained through significant gravitational deflection? The calculation requires careful geometry. You need to consider all possible orientations of the rotation axis in three-dimensional space. That's described by solid angles, essentially what fraction of all possible directions satisfy your constraints. If you have no constraints, all directions are equally probable, and you're covering the full sphere of possibilities. If you require the axis to point within some specific range of directions, you're only accepting a cone-shaped subset of that sphere, and the probability is the ratio of your cone's solid angle to the full sphere. For 3i Atlas, the constraints are these. The rotation axis must be aligned closely enough to the sun's direction that a jet emanating near one of the rotational poles can wobble, while still maintaining sun-pointing behavior on average. The observed wobble amplitude tells you how far from the exact pole the active region can be. The observed stability through perihelion tells you how precisely the axis must track the sun's direction as the trajectory curves. When you work through the geometry, you find that you need the rotation axis to be aligned within roughly 8 degrees of the sun's direction. Not 8 degrees of arc wobble room, 8 degrees of average alignment tolerance for the axis itself. And you need the active region to be offset from the rotational pole by less than about 8 degrees of latitude on the object's surface. These are the constraints that allow the observed wobble pattern and sun-tracking behavior to coexist. Now calculate the probability. Take all possible directions the rotation axis could point in three-dimensional space. That's a full sphere of directions, containing solid angle of 4 pi steradians. Now take only those directions within 8 degrees of the sun's direction. That's a cone with a half angle of 8 degrees, containing solid angle of approximately 2 pi times 1 minus cosine of 8 degrees. Do the division, and you get the fraction of all possible random orientations that satisfy the axis alignment constraint. The number is about 0.5%, 1 in 200. That's the probability that random initial conditions would place the rotation axis within the required tolerance to produce what we're observing. And this probability calculation doesn't even include the additional constraint that the active region must be at the right latitude near the pole. Including that constraint would make the probability smaller still. Less than 1 in 200 natural objects should, by random chance, be configured the way 3i Atlas is configured, and that's before you factor in the additional improbability that this rare configuration would be maintained through significant gravitational deflection, according to Loeb's interpretation of the post-perihelion observations. It's before you account for the 14 other anomalies that researchers have documented, each adding its own layer of statistical implausibility to the natural explanation. This is the smoking gun that Avi Loeb and his colleagues presented to the scientific community. Not speculation about alien technology, not wishful thinking or motivated reasoning, just straightforward probability theory applied to precisely measured geometric constraints. And the result is a number that forces honest scientists to admit that either we're witnessing a remarkably improbable, natural configuration, or we need to seriously consider alternative explanations that don't rely on random chance. The 0.5% probability doesn't prove anything by itself. Rare events happen. If you observe enough objects, eventually you'll see 1 in 200 configurations just by chance. But 3i Atlas isn't one of thousands of similar objects where we'd expect rare configurations to appear occasionally. It's only the third confirmed interstellar visitor, and it happens to display the most precisely aligned, most improbably configured geometry of any comet-like object we've studied in detail. The odds of that combination, rare object, rare configuration, stack multiplicatively into realms that strain coincidence as an explanation. And this brings us to the most profound question this discovery raises. That 0.5% doesn't exist in isolation. It's part of a larger pattern of anomalies, each one adding evidence to the case that something genuinely unprecedented is occurring. So what are those 14 anomalies that researchers have documented? What does this alignment geometry actually mean for the object's physical configuration? And why would maintaining one side facing the Sun be a desirable feature for something travelling through our solar system? When scientists talk about anomalies in astronomical observations, they're usually referring to minor deviations from theoretical predictions, small discrepancies that point toward refinements in our models, or subtleties we hadn't previously accounted for. An orbit that's slightly different than calculated might reveal an unseen moon, or a minor asymmetry in the parent body's gravity field. Unexpected spectral lines might indicate unusual composition or temperature gradients. These anomalies are the bread and butter of observational science. They're how we learn, how we improve our understanding, how we discover new physics when necessary. But what happens when the anomalies start accumulating? When you don't have 1 or 2 minor discrepancies, but 14 distinct lines of evidence all pointing toward the same disturbing conclusion? That's where 3i Atlas has pushed the scientific community. This isn't about one measurement that seems odd. This is about a pattern of behavior that systematically violates expectations across multiple independent observational modes and analysis frameworks. The 0.5% probability represents what Loeb identifies as the 14th of these anomalies, and it's the one that ties many of the others together into his interpretation of a coherent pattern. So before we dive into what that probability specifically measures, let's understand what it means for an object to have 14 separate anomalies. Each one independently raises questions. Together they create a case that becomes difficult to dismiss with conventional explanations. The anomalies span different aspects of the object's behavior and properties. Some relate to its trajectory and non-gravitational accelerations. Some concern the nature and geometry of its outgassing. Some involve the temporal patterns observed in brightness and jet activity. Some deal with the object's rotation and orientation. And crucially, these anomalies aren't subjective judgments. They're quantifiable departures from what models predict for natural comets, with similar orbital parameters and observational circumstances. When Avi Loeb's research team compiled this list of anomalies in his published analyses, he argues they weren't cherry-picking unusual features while ignoring conventional aspects. They were documenting every way in which 3i Atlas differs from the population of well-studied comets we use as our reference class. And what emerged from that documentation was a profile that sits far outside the normal distribution of cometary properties. Not just unusual, statistically outlying to a degree that demands explanation. The 14th anomaly, the one we've been building toward throughout this investigation, concerns the specific geometric configuration required to produce the observed behavior. Remember the constraints we discussed. Rotation axis aligned within roughly 8 degrees of the Sun's direction. Active region located within 8 degrees of a rotational pole. These aren't vague requirements. They're precise geometric boundaries derived from detailed analysis of the observational data. But here's what makes this anomaly different from simply having an unusual alignment. It's not just that the axis points toward the Sun right now at this moment. It's that this alignment has persisted over the entire observational baseline, through significant changes in the object's trajectory, and appears stable going forward. That persistence, that stability through perturbations, is what pushes the probability down to 0.5%. Think about the difference between a snapshot and a movie. If you take a random photograph of people walking on a busy street and notice that 2 people are facing exactly toward each other, that's mildly interesting but not shocking. Random configurations occasionally produce patterns. But if you watch video footage and see those same 2 people maintain eye contact, while weaving through crowds, turning corners, climbing stairs, always keeping their faces oriented toward each other. Despite all the obstacles and path changes, you'd start suspecting they're deliberately maintaining that connection. The persistence of the pattern over changing circumstances is what distinguishes coincidence from coordination. 3i Atlas has maintained its sun-pointing alignment through changing circumstances. The object's distance from the Sun has varied dramatically, from beyond the orbit of Mars down to perihelion passage closer than Earth's orbit, and back outward. The Sun's gravitational influence has varied accordingly, causing significant trajectory deflections. The intensity of solar radiation heating different parts of the object's surface has changed by orders of magnitude. Through all of these variations, the geometric configuration that allows the anti-tail jet to point sunward has remained stable. That stability is what the 0.5% probability quantifies. It's not just asking, what are the odds of this particular configuration? It's asking, what are the odds that random initial conditions would produce a configuration this stable, this resistant to perturbation, this precisely maintained over the timescale and circumstances we've observed? Now let's understand what this configuration actually means for the object's physical state. If the rotation axis is aligned toward the Sun, and the dominant active region is near one of the rotational poles, then the object has a well-defined sunward-facing side and an opposite anti-sunward side. As the object rotates, the same hemisphere continuously faces the Sun, while the opposite hemisphere remains in perpetual darkness. This is exactly analogous to tidal locking, where one face of a moon always points toward its planet, but achieved through rotational axis alignment rather than tidal forces. This configuration creates what engineers would call a sun-synchronous orientation, where the thermal and radiation environment on the object's surface is divided into distinct zones. One side receives continuous solar heating and illumination. The opposite side is continuously shadowed and cold, and if the active region producing the anti-tail is on the sunward side near the pole, it's positioned exactly where you'd place a sensor or instrument if you wanted continuous, unobscured observation of the Sun. The implications of this geometry are profound. Natural comets don't develop stable sun-synchronous orientations. Their rotation axes are randomly oriented initially, and evolve unpredictably as outgassing torques accumulate over time. The rotation periods change, the axis direction wanders, the surface features producing jets migrate or shut down as composition varies. You get chaotic evolution, not stable configurations maintained over months of observation. But if you were designing an interstellar probe intended to study a star, sun-synchronous orientation would be high on your list of desirable features. You'd want your instruments aimed reliably at your target. You'd want stable thermal conditions for your equipment, not the wild temperature swings that a randomly tumbling object experiences. You'd want predictable power delivery if you're using solar panels, and you'd accept some wobble from your rotation, because perfect attitude control requires heavy gyroscopes or reaction wheels, and mass is precious on interstellar missions. This is the uncomfortable parallel that keeps emerging from the data. The observed configuration isn't just improbable for natural objects, it's optimal for designed systems with specific observational goals. And when improbable and optimal align in the same configuration, coincidence becomes harder to defend as the primary explanation. Let's address the elephant in the room. Saying something is improbable is not the same as saying it's impossible. A 0.5% probability means that if you observed 200 randomly configured objects, you'd expect to see this configuration about once. So why not accept that we simply got lucky, that 3i Atlas happens to be that 1 in 200 case, and move on with conventional explanations? The answer lies in base rates and priors. If interstellar objects were common, if we detected hundreds of them per year, then seeing one with a 1 in 200 configuration would be expected and unremarkable. But we don't detect hundreds per year. We've confirmed 3 in 8 years, given that base rate. The prior probability that any particular interstellar object would show a 1 in 200 configuration is extremely low, and when you multiply that already low prior by the conditional probabilities of the other 13 anomalies, you get combined odds that strain statistical reasoning. There's a principle in statistics called the multiplication of improbabilities. When independent improbable events must all occur together to produce an observation, you multiply their individual probabilities to get the combined likelihood. If 13 anomalies each have, say, a 5% chance of occurring individually, the probability of seeing all 13 in one object is 0.05 raised to the 13th power, which is a number so small it's effectively zero. Now, the anomalies documented for 3i Atlas aren't fully independent. Some are correlated with others because they arise from the same underlying configuration, but even accounting for correlations, the combined improbability of the full anomaly profile is staggering. You're not just explaining away one unusual measurement, you're explaining away a coherent pattern of anomalies that all happen to point toward the same interpretation: active orientation control maintaining sun-synchronous alignment. Avi Loeb has been careful to frame this finding in terms of hypothesis testing, rather than claims of proof. The 0.5% probability doesn't prove the object is artificial. What it does is establish that the natural explanation requires us to accept a significant statistical improbability. And in science, when one hypothesis requires accepting large improbabilities while an alternative hypothesis makes the observations expected rather than surprising, we're obligated to take that alternative seriously even if it challenges our preconceptions. The alternative hypothesis here is straightforward. 3i Atlas is maintaining sun-synchronous orientation because it was designed to do so. The rotation axis alignment, the polar active region, the stability through perturbations, all of these features are exactly what you'd engineer into a probe intended for solar observation during a flyby through an alien star system. The wobble is an acceptable consequence of using rotation for some level of passive stabilization rather than heavy active control systems. The 0.5% probability isn't a problem to explain away, it's a specification tolerance, the margin within which the control systems are designed to maintain alignment. Under this hypothesis, the 14 anomalies aren't 14 separate coincidences requiring 14 separate explanations. They're 14 observable consequences of a single underlying fact: intentional design for specific functional goals. This is what scientists call explanatory parsimony. One assumption, that the object is artificial, explains multiple independent observations more economically than invoking 14 different natural explanations that must all happen to occur together in one object. Parsimony doesn't equal truth. A simple explanation can be wrong while a complex explanation is correct. But parsimony is a guide in situations where we lack definitive direct evidence. And right now, we lack that definitive evidence. We can't land on 3i Atlas, we can't retrieve samples, we can't examine its surface to look for manufactured structures or materials. All we have are remote observations, photons collected by telescopes millions of kilometers away, analyzed with models and statistics and geometric reasoning. Given those limitations, the 0.5% probability stands as the single most quantifiable piece of evidence that something unprecedented is occurring. It's not subjective. It's not based on interpreting ambiguous patterns. It's straightforward geometry and probability theory applied to precise measurements, and it forces a decision point. Either accept that we're witnessing a genuinely rare natural configuration that happens to mimic engineered design, or seriously entertain the possibility that the mimicry is because we're actually observing engineered design. The scientific community remains divided on this decision. Some researchers find the improbability compelling enough to warrant serious consideration of the artificial hypothesis. Others argue that extraordinary claims require extraordinary evidence, and that statistical improbability alone isn't sufficient to invoke alien technology. Both positions have merit. Both reflect legitimate approaches to evaluating evidence under uncertainty. What's not debatable is that the probability is what it is: 0.5%, 1 in 200. You can argue about what that number should make us believe, but you can't argue with the geometric calculations that produced it. The rotation axis is aligned with the Sun to within the measured tolerance, or it isn't. The active region is located near the pole, or it isn't. The configuration has remained stable through perihelion deflection, or it hasn't. These are matters of observational fact, and the facts support the calculation. So now we arrive at the central question this investigation must address. Given that we're observing something with a 0.5% probability of occurring naturally, something that displays 14 documented anomalies, something that maintains a sun-synchronous orientation that looks optimized for solar observation, what explanations can account for all of this? Can natural processes, understood correctly and applied carefully, still explain 3i Atlas without invoking design? Or have we reached the point where the artificial hypothesis deserves equal consideration alongside natural alternatives? Science progresses through a careful dance between skepticism and openness. We demand rigorous evidence before accepting new ideas, but we must remain willing to follow evidence wherever it leads, even into uncomfortable territory. When it comes to 3i Atlas, that territory involves asking questions that challenge our fundamental assumptions about our place in the universe and whether we've truly been alone in the cosmos or simply unaware of what's been passing through our solar system all along. Let's start with the natural explanations, because any honest evaluation of extraordinary claims must begin by thoroughly exploring conventional possibilities. What natural processes could produce the observed behavior of 3i Atlas without requiring us to invoke alien technology or intentional design? The first category of natural explanations involves unusual but not impossible composition and structure. Perhaps 3i Atlas has an extremely non-uniform internal composition, with volatile material concentrated in one region near what happens to be a rotational pole. As this region outgasses preferentially when heated by the sun, it could produce a dominant jet while other parts of the object remain relatively inactive. The jet's thrust, if it happens to be roughly aligned with the rotation axis, would create minimal torque on the object's spin, allowing the axis orientation to remain relatively stable. This explanation has some merit. We know comets are not homogeneous bodies. They're rubble piles, loose agglomerations of material that are accreted in the cold, outer regions of protoplanetary disks. Different regions can have very different compositions, and it's plausible that an interstellar object, formed around a different star with different chemistry, could have more extreme compositional variations than typical solar system comets. But this explanation struggles with the persistence and precision of the alignment. Even if you start with a favourable configuration, axis aimed sunward, active region at the pole, small perturbations accumulate over time. Every slight asymmetry in the outgassing, every tiny torque from uneven heating, every gravitational gradient during close approach to the sun adds up. Natural systems don't maintain precise configurations without restoring forces that push them back toward equilibrium when disturbed. What would provide such restoring forces for 3i Atlas? Some researchers have suggested that the outgassing itself could provide stabilizing feedback through a phenomenon called jet torque. Recent studies have also shown that non-gravitational forces on comets can be more complex than previously modelled, potentially explaining unusual trajectory behaviours through natural processes. If the active region is offset slightly from the rotational pole, the jet's thrust creates a small torque. Depending on the geometry and timing, this torque could potentially nudge the rotation axis back towards sun alignment if it starts to drift. It's a self-correcting mechanism, passive feedback from basic physics rather than active control. The challenge with this explanation is the precision it requires. Jet torque feedback is sensitive to many parameters: the exact location and orientation of the active region, the magnitude and timing of outgassing, the object's moment of inertia and spin rate. Getting all these parameters to produce stabilizing rather than destabilizing torques, and maintaining that favorable configuration over months of observation through large changes in solar heating, requires an improbable alignment of factors. You've essentially traded one improbability for another. Instead of improbably precise initial conditions, you have improbably precise fine-tuning of physical parameters. Another natural explanation focuses on the object's rotation state. Perhaps 3i Atlas is in a special dynamical configuration called a spin-orbit resonance, where the rotation period is synchronized with some aspect of its orbital motion. Earth's moon is tidally locked to Earth through such a resonance. One face always points toward our planet, because the rotation period exactly matches the orbital period. Could something similar be happening with 3i Atlas and the Sun? The problem is timescale. Tidal locking occurs through gradual energy dissipation, over long periods, millions of years for moons orbiting planets. 3i Atlas has been in our solar system for less than a year, hardly enough time for tidal forces to establish any synchronization. And more fundamentally, the object is on a hyperbolic trajectory. It's not orbiting the Sun, it's passing through once and will never return. Resonances require repeated orbital periods to establish and maintain. You can't tidally lock something that's just visiting. What about magnetic interactions? The Sun has a powerful magnetic field that extends far into space, carried by the solar wind. If 3i Atlas has its own magnetic field and contains materials that can interact with the Sun's field, could magnetic torques be orienting the object? This mechanism has been suggested for certain asteroids in our solar system that show unusual rotation behavior. It's an intriguing idea, but the torques would need to be substantial to reorient a comet-sized object over the timescales observed. That requires either very strong magnetic fields or large magnetic moments in the object itself. Comets are not particularly magnetic. They're made of ice, dust, and rock, none of which are strongly magnetic materials. You'd need something unusual in the composition, perhaps metallic cores or magnetic minerals far more abundant than typical cometary material. Again, you're invoking special circumstances stacked on special circumstances. Each natural explanation we examine has this same characteristic. It's not impossible, but it requires specific conditions, fortunate configurations, or fine-tuned parameters. Individually, each assumption might be plausible, but explanations that require 3 or 4 or 5 independent assumptions, all of which must be true simultaneously, become progressively less satisfying. At some point, you're fitting the theory to the observations with so many adjustable parameters that you've lost the predictive and explanatory power that makes scientific theories useful. This is where the artificial hypothesis enters the conversation, not as wild speculation, but as a legitimate alternative that deserves evaluation alongside natural explanations. What would an artificial origin for 3I Atlas imply, and how well does that hypothesis account for the observations? If 3I Atlas is a manufactured object, a probe sent from another star system to study stars along its trajectory, then many of the puzzling features become expected rather than surprising. Maintaining sun-synchronous orientation is exactly what you design such a probe to do. The stable configuration through perihelion deflection is evidence of working attitude control systems, not an improbable natural coincidence. The 14 anomalies are design features, intentional choices made by whatever constructed the object to optimize its performance for solar observation. The rotation and wobble pattern makes sense for a probe using spin stabilization, a common technique in spacecraft design where rotation provides gyroscopic stability, while instruments are mounted near the spin axis to minimize their motion relative to the target. The antitail could be deliberate thrust for trajectory corrections or attitude control, or it could be waste heat and material being vented from onboard systems. The precise collimation could come from shaped nozzles, or magnetic confinement rather than natural gas expansion. Under the artificial hypothesis, you're not explaining 14 separate anomalies with 14 separate natural mechanisms. You're explaining them all with one underlying fact: intentional design by a technological civilization. This is explanatory economy at work, and it's worth noting that the features we're observing are exactly the features that human engineers would incorporate if we were designing an interstellar probe to study other stars. The parallels are striking because the engineering requirements are universal. Physics doesn't change from one star system to another. But extraordinary claims require extraordinary evidence. Saying that an object might be artificial is very different from proving it is. What would constitute proof? Ideally, we'd detect unambiguous technological signatures, radio transmissions, artificial materials visible in spectroscopy, geometric structures resolved in high-resolution imaging. We haven't detected any of those things with 3I Atlas, and that absence is significant. However, the absence of obvious artificial signatures doesn't disprove the artificial hypothesis. An interstellar probe might be designed for passive observation without active transmissions. It might use materials that don't produce unusual spectroscopic signatures at the distances and resolutions we're observing from. It might have smooth, aerodynamic shapes without obviously geometric structures. If you were designing a probe to travel through alien star systems without being immediately recognized as artificial, you might choose conservative designs that could plausibly be mistaken for natural objects by civilizations that weren't looking carefully. This is the razor's edge that 3I Atlas walks in our analysis. The object is anomalous enough to raise serious questions, but not obviously artificial enough to force conclusions. It occupies the uncomfortable middle ground where both natural and artificial explanations face challenges. Natural explanations require stacking improbabilities. Artificial explanations require accepting the profound implications that would follow from confirming technological artifacts from another civilization. Avi Loeb has advocated for treating both possibilities with equal seriousness. He points out that we've historically been too quick to dismiss unusual observations that might indicate extraterrestrial technology, partly because of the stigma attached to the topic, and partly because of legitimate concerns about credibility and career consequences in the scientific community. But science should follow evidence, not social pressures. If the evidence suggests we should consider artificial origin seriously, then we should do so while maintaining the same rigorous standards we apply to any hypothesis. Other scientists, including comet specialists like Dr. Matthew Knight, counsel caution, arguing that we should exhaust all natural explanations before invoking artificial ones. They point out that with only 3 confirmed interstellar objects, we don't yet have enough data to know what's normal for objects formed in other stellar systems, with potentially very different compositions and histories than solar system bodies. This position reflects the principle that extraordinary claims require extraordinary evidence. If there's any plausible natural explanation, even one that requires unlikely circumstances, we should prefer it over the radically paradigm-shifting conclusion that we're observing alien technology. This conservative approach has served science well historically, preventing premature acceptance of revolutionary claims that later turned out to have conventional explanations. Both positions are defensible. Both reflect legitimate scientific values, boldness in following evidence versus caution about revolutionary claims. The tension between them is healthy, driving more careful observations, more rigorous analysis, and more thorough exploration of all possibilities. What matters is that the debate continues based on evidence rather than preconceptions, and that we remain open to wherever the data ultimately leads us. Right now, in December 2025, as 3i Atlas makes its closest approach to Earth before departing our solar system forever, we have a precious window to gather more data. Telescopes around the world are watching, collecting photons, measuring positions, analysing spectra. Every additional observation refines our understanding and helps constrain which explanations remain viable. And regardless of whether the ultimate answer is natural or artificial, the implications are profound, because what we're learning about 3i Atlas is changing how we think about interstellar objects, the prevalence of unusual phenomena in our cosmic neighbourhood, and the methods we should use to distinguish the genuinely extraordinary from the merely unusual. There's a moment in every scientific investigation when you step back from the details and ask what it all means for the bigger picture. We've spent thousands of words examining jets and wobbles and probabilities and alignment geometry. We've walked through the detective work that revealed 3i Atlas's unusual behaviour. Now we need to confront what this discovery implies, regardless of which explanation ultimately proves correct. If 3i Atlas is natural, then our understanding of cometary physics is incomplete in significant ways. We've studied comets for centuries, built comprehensive models of their behaviour, and felt confident that we understood the basic processes governing these icy wanderers. But a natural explanation for 3i Atlas would require physics or conditions we haven't previously encountered or properly accounted for. That's not a failure of science, it's how science progresses. Every anomaly that forces us to expand our models makes those models more accurate and comprehensive. What specific gaps would a natural 3i Atlas reveal? We'd need better understanding of how compositional asymmetries in comet nuclei affect rotational evolution and jet dynamics. We'd need to refine our models of how jet torques can produce stabilizing effects rather than chaotic tumbling. We'd need to investigate what range of initial conditions and physical properties can lead to sun-synchronous configurations, and how common those conditions might be among interstellar objects specifically versus solar system natives. These aren't idle academic questions. Understanding cometary behaviour has practical importance for planetary defence. Knowing whether and how potentially hazardous objects might deviate from predicted trajectories could be crucial for deflection efforts. It matters for planning future missions to comets, where we need to predict rotation states and outgassing patterns for safe rendezvous and sample return. And it matters for interpreting observations of comets around other stars, where we're detecting these objects at vast distances and need robust models to understand what we're seeing. More broadly, if interstellar objects like 3i Atlas exhibit behaviours we don't see in native solar system comets, that tells us something important about the diversity of planetary system conditions. Objects formed around different stars, in disks with different compositions and temperatures, might have properties that surprise us when they wander into our neighbourhood. The interstellar medium they travel through between stars might alter their surfaces in ways we haven't accounted for. Each interstellar visitor is a messenger carrying information about formation conditions elsewhere in the galaxy, and unusual messengers might carry the most interesting information. But if 3i Atlas were proven to be artificial, which remains unconfirmed and controversial, the implications would expand dramatically beyond cometary physics into the realm of humanity's place in the universe. Confirming that we've detected technology from another civilization would be arguably the most significant scientific discovery in human history. It would answer one of our deepest questions: are we alone? And it would raise 1,000 new questions about who created this object, where they came from, what they're trying to learn, and whether they know we're here. Think about what it would mean for an interstellar probe to be passing through our solar system right now, in December 2028, during the narrow window where we have sufficient astronomical technology to detect and analyze it. The timing seems remarkable. Just decades after we developed the capability to recognize unusual interstellar visitors, one arrives that pushes the boundaries of natural explanation. Is that coincidence? Or could there be more to that timing than random chance? Some researchers have speculated about the possibility of directed panspermia, or targeted exploration, where advanced civilizations send probes to star systems they've identified as potentially harboring life or technological species. Our solar system has obvious biosignatures visible in Earth's atmosphere: oxygen, methane, other gases, in combinations that don't occur in abiotic environments. An alien civilization scanning the galaxy with spectrographs centuries or millennia ago could have detected these signatures and sent a probe to investigate, with that probe arriving just as we've reached the technological level to notice it. This speculation ventures beyond what the evidence directly supports, but it illustrates the kind of thinking that becomes unavoidable once you seriously entertain the artificial hypothesis. You start asking not just, what is this object, but who made it and why? You start wondering about the civilization that could design and build interstellar probes, their level of advancement, their motivations for exploration, their potential awareness of our existence. And you confront the Fermi paradox from a new angle. If 3i Atlas is artificial, why haven't we detected others? Or have we, without recognizing them? How many objects that we've catalogued as natural comets or asteroids might actually be probes that didn't display obvious anomalies when we observed them? The idea that artificial objects might regularly pass through our solar system, unnoticed or dismissed as natural because we weren't looking for the right signatures, is both exciting and humbling. The December 19th closest approach to Earth represents a critical observation window. At its nearest point, 3i Atlas will be close enough that our best telescopes can resolve more details about its surface and structure. If there are geometric features or surface patterns that indicate artificial construction, this is when we're most likely to detect them. Multiple observatories have coordinated campaigns to maximize data collection during this window, using radio telescopes, optical instruments, and X-ray observatories to look for any unusual emissions or characteristics. The X-ray observations are particularly interesting. Natural comets generally don't emit significant X-rays unless they're interacting with the solar wind in specific ways. Artificial objects with power systems or active instruments might produce X-ray signatures from high-energy processes. Detecting unexpected X-ray emission could provide compelling evidence for technological activity. Conversely, the absence of such emission wouldn't disprove the artificial hypothesis. A well-designed probe might operate without producing detectable X-rays, but it would remove one potential line of evidence. Whatever we learn in the coming days and weeks, 3i Atlas has already changed how scientists think about interstellar objects. Future observations of similar visitors will be scrutinized more carefully for anomalies. We'll be developing better models that can distinguish natural variations from potentially artificial signatures. We'll be asking different questions and designing observation campaigns with the explicit goal of testing whether objects might be probes rather than assuming they're natural. This shift in observational strategy and theoretical framework is valuable regardless of 3i Atlas's true nature. Science advances by challenging assumptions and looking more carefully at what we might have previously taken for granted. The debate around this object has sparked exactly that kind of careful re-examination, pushing researchers to quantify what normal really means for cometary behavior, and how confidently we can distinguish anomalous from merely unusual. There's also a philosophical dimension to consider. Human civilization has long grappled with whether we're alone in the universe, whether intelligence and technology are common or extraordinarily rare among the stars. These questions touch on our sense of meaning and purpose, our understanding of how special or typical our existence might be. Scientific findings that bear on these questions resonate far beyond academic journals. They affect how we see ourselves and our place in the cosmos. If we confirm that 3i Atlas is artificial, that confirmation would ripple through our culture in unpredictable ways. It would validate the search for extraterrestrial intelligence as not just speculative but demonstrably relevant. It would raise questions about whether we should attempt communication, or whether detection is observation of a probe that completed its mission centuries ago. It would force serious consideration of what policies and protocols we should have for future similar discoveries. Even if we ultimately conclude the object is natural, having gone through this investigation seriously and rigorously is valuable. It establishes precedent for how to handle genuinely ambiguous cases where extraordinary explanations can't be dismissed out of hand. It shows that the scientific community can engage with controversial possibilities while maintaining rigorous standards. And it reminds us that the universe is large, ancient, and full of phenomena we haven't yet encountered or understood. The 14 anomalies of 3i Atlas will be studied for years to come, regardless of how we ultimately classify the object. Each anomaly teaches us something about the limits of our models and the range of behaviors that objects can exhibit under conditions we rarely observe. That's valuable knowledge, hard-won from careful observation and analysis, and it will inform how we interpret future discoveries as our observational capabilities continue improving. We stand at a unique moment in history. For the first time, we have the technology to detect and characterize interstellar visitors in detail. The sample size is still tiny, just 3 confirmed objects, but that number will grow. Each new detection gives us better statistics about what's normal versus anomalous for these visitors from beyond our solar system. Each one might be the one that provides definitive evidence, one way or another, about whether some of these objects are more than natural wanderers. And that brings us to the final question this investigation must address. Where do we go from here? What happens next with 3i Atlas as it departs our solar system? What should we be watching for, hoping to detect, prepared to discover in the final observations before this mysterious visitor disappears back into the interstellar void from which it came? Every great mystery deserves a resolution, but the universe doesn't always cooperate with our desire for tidy endings. As 3i Atlas continues its outbound journey from the inner solar system, moving farther from the Sun and Earth with each passing day, we face the reality that this object will soon become too faint and distant for detailed observation. Whatever we're going to learn, we need to learn it soon, during this narrow window, while the object remains observable with our most powerful instruments. The closest approach to Earth on December 19th represents the optimal moment for high-resolution observations. Astronomers worldwide have coordinated their efforts, scheduling telescope time on the most capable observatories to maximize the scientific return from this brief opportunity. Every wavelength of light carries different information. Visible light reveals surface properties and reflected sunlight. Infrared shows thermal emission and temperature distributions. Radio observations might detect unusual electromagnetic activity, and X-rays could indicate high-energy processes that natural comets don't typically produce. This coordinated campaign resembles the observation strategies used for other significant astronomical events, like asteroid close approaches or rare planetary alignments. But there's an added urgency with 3i Atlas because this isn't an object we'll see again. Unlike comets on elliptical orbits that return periodically, interstellar visitors are one-time opportunities. Miss the observation window, and the data is lost forever. What specific questions are scientists hoping to answer with these final observations? High on the list is better characterization of the object's shape and size. Knowing whether 3i Atlas is roughly spherical, elongated, or irregularly shaped would help constrain models of both natural and artificial origins. An extremely elongated shape might suggest an artificial structure, similar to the speculation around Oumuamua's unusual dimensions. A more typical irregular shape would be consistent with natural objects but wouldn't rule out artificial origins. Probes don't need to be obviously geometric. Surface properties matter too. Are there variations in brightness or colour across different regions of the object? Such variations could indicate compositional differences, which might help explain the unusual outgassing pattern. Or they might reveal patterns too regular to be natural, geometric features, or structures that would be smoking gun evidence for artificial construction. The resolution of our observations is limited by distance and the object's size, but even marginal detections of surface features could provide crucial clues. The continuation of the anti-tail jet will be monitored closely. Does it persist as solar heating diminishes with increasing distance? Does its intensity follow the expected curve for sublimating ice? Or are there anomalies in the brightness profile that might indicate something other than natural outgassing? If the jet suddenly ceases or dramatically changes behavior, that could indicate either natural processes like depletion of volatile material or potentially active control systems shutting down after completing their observation mission. Scientists are also watching for any trajectory changes not explained by gravity and known outgassing effects. If 3I Atlas makes trajectory adjustments that look like controlled thruster firings, discrete changes in velocity inconsistent with continuous outgassing, that would be powerful evidence for artificial systems. Natural objects don't make course corrections. They follow paths dictated by gravity and the momentum transfer from venting gases, both of which produce smooth, predictable effects rather than sudden maneuvers. The rotation state will continue to be monitored as well. Any changes in the rotation period or axis orientation beyond what natural torques should produce would be significant. If the sun-synchronous alignment breaks down now that the object is leaving the inner solar system, that might suggest the alignment was actively maintained only while solar observation was useful. If it persists indefinitely, that raises different questions about what mechanism maintains it over long timescales. Looking beyond the immediate observation campaign, 3I Atlas has already influenced how the scientific community approaches interstellar object detection and analysis. There are now formal proposals to establish dedicated survey programs specifically designed to find and characterize interstellar visitors, with rapid response observation protocols to catch them while they're still in the inner solar system where detailed analysis is possible. The Vera Rubin Observatory, coming fully online soon, will dramatically increase the detection rate of these objects. With its large mirror and wide field of view, it will scan the entire visible sky every few nights, catching transient events and moving objects that other surveys miss. Scientists estimate it could detect dozens of interstellar visitors per year once fully operational. That larger sample size will let us determine how unusual 3I Atlas really is, whether its anomalies represent genuine outliers or the extreme end of a broader distribution of behaviors. Future missions might even attempt to visit interstellar objects directly. There have been conceptual studies of fast-response spacecraft that could be launched to intercept visitors while they're still in our solar system, matching velocity to perform close flybys or even rendezvous. Such missions are technically challenging because of the high velocities and short warning times, but they're not impossible. If an object like 3I Atlas appeared again with more advance notice, a mission could potentially be organized. The ultimate fate of 3I Atlas itself is to leave our solar system and continue wandering through interstellar space, potentially for millions or billions of years, until it encounters another star system. If it's natural, it will gradually become dormant as it moves far from any heat source, a frozen relic drifting through the void. If it's artificial, it might reactivate when it approaches its next target star, beginning another observation campaign in a solar system light years from here, potentially recording data that some alien civilization will analyze centuries from now. There's something poetic about that image. A probe traveling between stars, spending brief intense periods of activity during stellar flybys, then hibernating through the vast empty stretches between systems. If such probes exist, and if they're numerous enough that we've detected one, then the galaxy might be crisscrossed with ancient explorers launched by civilizations that might no longer exist, continuing their programmed missions long after their creators are gone. We might be living in a galaxy far busier than it appears, filled with quiet observers we've only now begun to notice. That's the vision that 3I Atlas offers us, whatever its true nature. It reminds us that the solar system is not a closed box isolated from the rest of the cosmos. Objects pass through, carrying information about the broader galactic environment, perhaps occasionally carrying more than just ancient ice and rock. It challenges us to look more carefully at what we've been dismissing as routine, to question assumptions we didn't realize we were making, to remain open to discoveries that might fundamentally change our understanding of the universe and our place within it. This story isn't over. The observations continue, the analysis proceeds, and the debate about interpretation will likely persist for years. But you're witnessing this investigation in real time as it unfolds, at a moment when evidence is being gathered and debated that might someday, if Loeb's interpretation proves correct, be looked back on as the turning point where humanity first recognized we weren't alone. Or it might be remembered as the interesting anomaly that taught us important lessons about cometary physics and the diversity of interstellar objects. Either way, the 0.5% probability stands as a marker, a quantified measure of how unusual this object is, and a reminder that in a universe as vast and ancient as ours, even 1 in 100 chances eventually come up. The question is whether we're witnessing that rare natural roll of cosmic dice, or something that was never left to chance at all. Subscribe to follow what happens next as this investigation continues. Drop a comment and tell me, at what probability would you personally start taking the artificial hypothesis seriously? 5%? 1%? Or is 0.5% already well past that threshold? This conversation is just beginning, and whatever we learn from 3i Atlas is going to shape how we search the skies for years to come.